general, all measurable quantities are known as physical quantities, such as mass, length, time, current, and temperature. They are also known as fundamental quantities. To measure these quantities, we use different types of devices in different situations. The smallest quantity that can be measured with a device or an instrument is called the least count of that device. Some instruments that we use to measure length are the vernier calipers, rulers, and meter tapes. Similarly, we measure mass with the balance, time with the stopwatch, current with the ammeter, and temperature with the thermometer. The vernier caliper can measure up to 0.1 mm or 0.01 centimeter, while the plane scale or ruler can measure up to 1 mm or 0.1 centimeters. The devices that are used to measure mass are the common balance, digital balance, and analytical balance. The digital balance can measure up to 0.001 gram. You must have seen a digital balance in a jewelry shop. The common balance can measure mass up to 1 gram and is commonly used in grocery shops. There are devices that are used to measure time, such as the alarm clock, digital clock, and atomic clock. Atomic clocks and quartz clocks are used to measure time accurately. For example, in athletic meets and in scientific experiments. There is a new invention too, an optical atomic clock that ticks 1 million billion times every second and is at least 20 times more stable than current atomic clocks. All clocks consist of two basic mechanisms. One with the device called an oscillator, which produces periodic events moving the needle every second, and the second one for counting and displaying the time. The clocks that you have at home can measure time accurately up to 1 second. The ammeter is used to measure current. Nowadays, the multimeter is used to measure current up to 0.001 amps. Similarly, there is a device called the thermometer, which is used to measure temperature. Clinical thermometers and many electronic thermometers are usually readable to 0.1 degrees Celsius. Special instruments can give readings to 1,000th of a degree. Thus, these devices are useful to measure physical quantities accurately up to finite decimals.
To measure the length of an object. This scale is graduated in centimeters, and each centimeter is divided into 10 millimeters. We know that the smallest measure that can be measured accurately with a device is called least count of the device. Since the least count of an ordinary scale is 1 millimeter, it is not useful to measure the length or thickness of an object with great accuracy, that is, less than 1 millimeter. In such cases, a vernier calipers is used. The vernier calipers was invented by Pierre Vernier in the year 1960. It can measure length less than 1 millimeter. Let us calculate the least count of a vernier calipers. A vernier calipers consists of two scales. One is called the main scale or ordinary scale, which is fixed. The main scale is graduated in centimeter and millimeter. The other scale which slides along the main scale, is called the vernier scale. The vernier scale is graduated in divisions that are less than 1 millimeter. It is designed based on a principle such that n divisions on the vernier scale coincide with n-1 divisions on the main scale. Thus, the least count of the vernier calipers is equal to the difference between the values of one division on the main scale and one division on the vernier scale. That is, least count is equal to 1 MSD minus 1 VSD. The least count of vernier calipers is known as the vernier constant. Let the value of one main scale division be S and the value of one vernier scale division be V. From the principle of the vernier calipers, N into V is equal to N minus 1 into S. On simplifying, the equation can be written as S minus V is equal to S by N. Since the difference between one main scale division and one vernier scale division is equal to the least count of the vernier calipers, the least count can be written as S minus V, which is equal to S by N. This is equal to the value of one main scale division by the number of vernier scale divisions. Generally, in a standard vernier calipers, 10 vernier scale divisions coincide with 9 main scale divisions. Since the length of each main scale division is 1 millimeter, 10 divisions on the vernier scale are equal to 9 millimeter. Therefore, the value of one vernier scale division is equal to 9 by 10 millimeter, which is equal to 0.9 millimeter. Thus, the least count is equal to 1 millimeter minus 0.9 millimeter, which is equal to 0.1 millimeter. In another way, the least count is equal to one main scale division by the number of vernier scale divisions, which is also equal to 0.1 millimeter. Let us now take a look at the vernier calipers. A vernier calipers consists of a long, thin metallic strip called the main scale. The main scale is graduated in centimeter and millimeter. Each division on the main scale is equal to 1 millimeter. This metallic strip is provided with a jaw, J1, on the lower side at its end, which is called the fixed jaw. A metallic frame on the right side of the fixed jaw slides over the main scale, called the vernier scale. On the bottom edge of this frame is a graduated scale. It usually consists of 10 equal divisions that coincide with 9 main scale divisions. The value of each vernier scale division is equal to 0.9 millimeter. This vernier scale is provided with a jaw, J2, on the lower side, which can move with the vernier scale. This jaw is called the movable jaw. The vernier calipers is also provided with 2 more jaws, J3 and J4, on the upper side. J3 is attached to the main scale and J4 to the vernier scale. A screw S is attached to the main scale. It is used to fix the vernier scale at any position on the main scale. The jaws on the lower side, J1 and J2, are called the external jaws. These jaws can hold the object firmly and help to measure the length of a rod, diameter of a sphere, and external diameter of a cylinder, etc. The jaws on the upper side, J3 and J4, are called the internal jaws and are used to measure the internal diameter of a hollow cylinder. A thin and long strip T is attached to the vernier scale at the back of the main scale. This strip is called the tail and is used to measure the depth of hollow cylinders and small beakers. Further, the main scale and the vernier scale are also graduated in inches, which helps in measuring dimensions in inches. Let us now see how the length of an object is measured using the vernier calipers. The object is held by the external jaws of the object, such that the readings on the main scale and the vernier scale are as shown in the figure. From the figure, it is clear that the length of the object is AB. AB can be written as the sum of AC and CB, where AC is the main scale reading, MSR, and CB is the fractional reading, which can be determined with the help of the vernier scale. The fractional reading CB is equal to CD minus BD. Note down the number of the division on the vernier scale that exactly coincides with the definite main scale division. This division is called the vernier coinciding division, VCD. Let this be N. From the figure, CD is equal to N main scale divisions. BD is equal to N vernier scale divisions. Then, CB is equal to N main scale divisions minus N vernier scale divisions. On taking N common, CB can be written as N into 1 main scale division minus 1 vernier scale division. You know that the difference between 1 main scale division and 1 vernier scale division is equal to the least count. Therefore, CB can be written as N into least count. But N is the vernier coinciding division. Therefore, the fractional reading, CB, is equal to vernier coinciding division into least count. The length of the object, AB, is equal to main scale reading plus fractional reading, which is equal to main scale reading plus vernier coinciding division into least count. Before measuring the length of an object using the vernier calipers, you need to check whether the instrument is error-free. Bring the two external jaws, J1 and J2, in contact. If the 0 on the main scale coincides with the 0 on the vernier scale, then the vernier calipers is free from error. In this condition, the tail of the vernier calipers just touches the end of the main scale strip. If the 0 on the main scale does not coincide with the 0 on the vernier scale, then the vernier calipers is said to have zero error. There are two types of zero errors. They are positive zero error and negative zero error. With the two external jaws in contact, if the 0 of the vernier scale is on the right side of the 0 of the main scale, then the zero error is said to be positive. The error is equal to the distance between the main scale 0 and the vernier scale 0. The positive zero error is equal to the vernier coinciding division into least count. The correction for a positive zero error is equal to minus of positive zero error. To get the correct reading, the correction should be added to the observed reading. Thus, corrected reading is equal to observed reading plus positive zero correction. For example, when the two external jaws are brought in contact, if 0 of vernier scale is on the right side of the 0 of the main scale, and fourth division on the vernier scale coincides with one of the main scale divisions, and least count of the vernier calipers is 0.1 millimeter. In this case, the positive zero error is equal to 4 into 0.1 millimeter, which is equal to 0.4 millimeter. Thus, the positive zero correction will be minus 0.4 millimeter. When the two external jaws are in contact, if the zero of the vernier scale is on the left side of the zero of the main scale, then the zero error is said to be negative. The error is equal to the distance between the main scale 0 and the vernier scale 0. The negative zero error is equal to minus of total number of divisions on the vernier scale minus vernier coinciding division into least count. The correction for a negative zero error is minus of negative zero error. To get the correct reading, the correction should be added to the observed reading. Thus, the corrected reading is equal to observed reading plus negative zero correction. For example, when the two external jaws are kept in contact, the zero of the vernier scale is on the left side of the zero of the main scale, and the seventh division on the vernier scale coincides with one of the main scale. The number of divisions on the vernier scale is 10, and the least count of the vernier calipers is 0.1 millimeter. The negative zero error is equal to minus of 10 minus 7 into 0.1 millimeter, which is equal to minus 0.3 millimeter. Then, the positive zero correction is equal to minus of minus 0.3 millimeter, which is equal to 0.3 millimeter. Let us now see how to measure the length of a cylindrical rod. First, find the least count, LC, of the vernier calipers. Bring the two external jaws in contact and check the position of 0 on the main scale and the vernier scale to see if there is any error. If there is any error, then note it down and calculate the zero correction. The movable jaw, G2, is moved and the cylindrical rod whose length is to be measured is placed between the two external jaws. Now the vernier scale is fixed by tightening the screw S. Note the reading on the main scale just before the zero of the vernier scale, which gives the main scale reading MSR in centimeter. Note down the division on the vernier scale that coincides with any one of the divisions on the main scale. This gives the vernier coinciding division VCD. Multiply the vernier coinciding division with the least count and convert it into centimeter. The observed reading is equal to main scale reading plus vernier coinciding division into least count. The corrected reading is equal to observed reading plus zero correction. Repeat the procedure by placing the object in different positions along its length. The readings are tabulated as shown. The average of the corrected readings gives the length of the object accurately. To find the inner diameter of a hollow cylinder, fix the cylinder to the internal jaws and follow the same procedure. Similarly, to find the depth of a hollow cylinder or a small beaker, place the tail of the vernier calipers along its depth and follow the same procedure. Know that you can use an ordinary scale to measure up to 1 millimeter accurately. You also know that you can use the vernier calipers to measure up to 0.1 millimeter accurately. The least count of the vernier calipers is 0.1 millimeter. Therefore, you cannot use it to measure any dimension less than 0.1 millimeter accurately. A screw gauge is used in such cases. It is used to measure up to 0.01 millimeter with greater accuracy. Thus, it can be used to measure the thickness of thin objects like wires, glass sheets, and so on. The screw gauge works on the principle of a screw in a nut. The screw gauge consists of a U-shaped metallic frame. One end of this U-frame has a fixed flat shaft, called the stud or anvil. It forms the fixed jaw of the screw gauge. The other end of the U-frame has a long hollow cylinder with fine threads inside. This serves as the nut. This cylinder is called the sleeve cylinder. On the outer surface of the sleeve cylinder, a line parallel to the axis of the cylinder is engraved. This line is called the index line or base line. The index line is graduated in millimeters or half millimeters. This is called the pitch scale or main scale. There is a screw with a flat tip and threads on its outer side, identical to the threads cut inside the sleeve cylinder. This is called the spindle. The spindle moves inside the sleeve cylinder. The flat tip of the spindle is nothing but a shaft which forms the movable jaw of the screw gauge. The other end of the spindle is connected to a milled head. To the milled head, one end of another hollow cylinder is connected. This hollow cylinder is called the barrel. The other end of the barrel is tapered and graduations are made. There are either 50 or 100 equal divisions on it. This is called the head scale, circular scale, or thimble. The end of the screw is connected to a ratchet by means of a spring. When the flat tip of the screw comes in contact with the stud, the ratchet becomes free and makes a rattling sound. Thus, the tip of the screw cannot be pushed further towards the stud. The screw gauge is also provided with a lock nut, which holds the scales at a particular position to prevent errors. Let us now measure the diameter of a metal wire. Before making a measurement, you should first determine the pitch of the screw, the least count, and zero error of the instrument. When the head of the screw is rotated, the tip of the screw moves either forward or backward. The distance traveled by the tip of the screw in one complete rotation of its head is called the pitch of the screw. This distance is equal to the separation between two adjacent threads on the screw and parallel to its axis. To find the pitch of the screw, rotate the head of the screw till the zero of the head scale coincides with any one of the divisions on the pitch scale. Let us say the head scale is at 5 mm. Then turn the head scale, which has 100 divisions on it, by a certain number of rotations, say 5. After 5 rotations, the zero of the head scale is at 10 mm on the pitch scale. Note the distance travelled by the screw in 5 rotations. Here, it is equal to 5 mm. Then the pitch of the screw is equal to the distance travelled by the screw on the pitch scale divided by the number of rotations made by the head scale. Therefore, the pitch of the screw is equal to 5 mm by 5, which is equal to 1 mm. Using the pitch of the screw, let us calculate the least count of the screw gauge. You know that least count is the smallest measure that can be made accurately by an instrument. When the head scale is rotated such that only one division on the head scale crosses the index line, the distance travelled by the head scale along the index line is called the least count. In another way, the least count is equal to the pitch of the screw divided by the number of head scale divisions. As the pitch of the screw is 1 mm and the number of head scale divisions are 100, the least count of the screw gauge is 1 millimeter by 100, which is equal to 0.01 millimeter. Before making a measurement, you must also check if the screw gauge has any zero error. Rotate the head scale such that the tip of the screw is in contact with the stud. If the zero of the head scale coincides with the index line of the pitch scale and the head scale is exactly on the zero of the pitch scale, then the screw gauge has no zero error. However, if the zero of the head scale does not coincide with the index line, then the screw gauge is said to have zero error. There are two types of zero errors. They are positive zero error and negative zero error. When the tip of the screw is in contact with the stud, if the zero of the head scale is below the index line of the pitch scale, then the error is said to be positive zero error. If n is the coinciding division of the head scale with the index line of the pitch scale, then the positive zero error is equal to n into least count. Then the positive zero correction is minus of positive zero error. That is, the correction for positive zero error is negative. For example, if the sixth division on the head scale coincides with the index line of the pitch scale and the least count of the screw gauge is 0.01 millimeter, then the positive zero error is equal to 6 into 0.01 millimeter, which is equal to 0.06 millimeter. Then the positive zero correction is minus of positive zero error, which is equal to minus 0.06 millimeter. When the tip of the screw is in contact with the stud, if the zero of the head scale is above the index line of the pitch scale, then the error is said to be negative zero error. If n is the coinciding division of the head scale with the index line of the pitch scale, then the negative zero error is equal to minus of number of divisions on the head scale minus n into least count. Then the negative zero correction is minus of negative zero error. That is, the correction for negative zero error is positive. For example, if the 96th division of the head scale coincides with the index line of the pitch scale, the total number of divisions on the head scale is 100 and the least count of the screw gauge is 0.01 millimeter. Then the negative zero error is equal to minus of 100 minus 96 into 0.01 millimeter, which is equal to minus 0.04 millimeter. Then the negative zero correction is equal to minus of minus 0.04 millimeter, which is equal to 0.04 millimeter. Now let us measure the diameter of a wire with a screw gauge. After calculating the pitch of the screw, least count and zero error, if any, rotate the head scale anti-clockwise so that the shafts open. Place the wire between the stud and the tip of the screw. Rotate the ratchet clockwise so as to hold the wire tightly between the stud and the tip of the screw. Note the reading on the index line just before the head scale. This is the pitch scale reading or main scale reading. Note the reading on the head scale that coincides with the index line of the pitch scale. This reading is called head scale reading or circular scale reading. The observed diameter of the wire is equal to pitch scale reading plus head scale reading into least count. To get the correct diameter of the wire, the positive zero correction or the negative zero correction of the device should be added to the observed diameter of the wire. Repeat the procedure by taking readings at 4 or 5 different parts of the wire and tabulate the readings. The average of the corrected diameters gives the actual diameter of the wire. Sometimes, due to wear and tear of the threads of the screw, the tip does not reverse immediately on rotating the head scale back. This is called backlash. This causes an error in the observation and is called backlash error. To avoid backlash error, the screw should be rotated in one direction only. We have seen different types of substances, such as solids, liquids, and gases. The space occupied by a substance is called its volume, which is denoted by V. The unit for volume in the MKS and SI systems is meter cube or cubic meter. 1 meter cube is defined as the volume of a cube of side 1 meter each. In the CGS system, the unit for volume is centimeter cube or cubic centimeter. 1 centimeter cube is defined as the volume of a cube of side 1 centimeter each. 1 meter cube is equal to 10 to the power 6 centimeter cube. A gas does not have definite volume. It occupies the total volume of the container in which it is filled. However, liquids and solids have definite volumes that can be measured. Let's see how the volume of a liquid and a solid is measured. Solids have a definite shape and size. But liquids do not have any particular shape. They take the shape of the container into which they are poured. The volume of liquids is measured in liters and milliliters. 1 liter is equal to 1000 milliliters. 1 liter is defined as the volume of 1 kilogram of pure water at 4 degrees Celsius and normal atmospheric pressure. Although the liter is not an SI unit, it is accepted for use with the SI. When we take a liquid in narrow tube, it forms a curved surface. The curved surface is called meniscus. The surface of all liquids, except mercury, curves downwards. This is called concave meniscus. On the other hand, the surface of mercury curves upwards, which is called convex meniscus. Hence, while measuring the volume of liquids in narrow tubes, take the reading at the lower meniscus for all the liquids except mercury and at the upper meniscus for mercury. The reading should be taken without parallax error. To avoid parallax error, place your eye at the level of the lower meniscus for all the liquids except mercury, and at the level of the upper meniscus for mercury. The apparatus used to measure the volume of a liquid are the measuring cylinder, measuring flask, pipette, burette, etc. We will now study these apparatus in detail. The measuring cylinder is a glass cylinder graduated into milliliters and cubic centimeters. Pour the given liquid carefully into the measuring cylinder so that no air bubbles are trapped inside. Note down the reading against the level of the liquid without any parallax error. This reading gives the volume of the given liquid. The graduations on the measuring cylinder indicate the volume of the liquid. Let us now look at the measuring flask. There are 2 types of measuring flasks, round-bottomed and flat-bottomed. The measuring flask consists of a long, narrow neck provided with a stopper. A graduation mark is etched on the neck. If the measuring flask is filled with a liquid up to the graduation mark, it contains a fixed volume which is indicated over the flask. Measuring flasks are available in different capacities like 50 milliliters, 100 milliliters, 250 milliliters, and so on. Another measuring device is the pipette. The pipette is used to measure a definite volume of liquid. It is generally used to transfer a definite quantity of liquid from one vessel to another. It consists of a cylindrical glass bulb with narrow glass tubes above and below it. The lower end of the glass tube is tapered. A graduation mark is etched on the stem. The liquid filled in the pipette up to this mark represents its capacity, which is indicated over the glass bulb. To measure a definite volume of a given liquid, immerse the narrow end of the pipette into the given liquid. Hold the stem of the glass tube and suck the liquid till its level rises a little above the mark on the glass stem. Be careful not to suck the liquid into your mouth. Now cover the mouth of the pipette with your finger. Hold the pipette vertically and release the finger slowly till the level of the liquid comes to the mark on the glass stem. Then close the finger and introduce the pipette into a beaker and release the finger. The liquid in the pipette runs down into the beaker, but a little of it remains in the narrow end. This can be collected by tapping the tip of the pipette against the beaker. By using a pipette, we can collect only a fixed amount of liquid. We cannot collect the fractions of the volume displayed on the bulb. To collect fractions of a certain volume, we use another device called the burette. The burette is a long cylindrical tube with a nozzle at one end. The cylindrical tube is graduated in milliliters or cubic centimeters. The volume of the liquid to be collected can be controlled with the help of a tap fixed at the nozzle. The burette is clamped in a vertical position to a stand and is filled with the liquid. Open the tap and allow a little liquid to run down, and then close it to let the air in the nozzle run out. To collect some volume of the liquid in a beaker, place the beaker below the nozzle. Note the original level of the liquid in the burette. Open the tap and transfer some liquid into the beaker, and then close the tap. Note the level of the liquid in the burette again. The difference between the readings gives the volume of the liquid transferred into the beaker. There are many other devices to take fixed volume of liquids. They are the conical flask, measuring vessel, etc. Coming to solids, they are regular or irregular in shape. If a given solid substance is regular in shape, its volume can be found by measuring its dimensions and substituting the values in the formula for volume of the corresponding shape. Let us see the formulae for the volume of some regular shaped objects. The volume of a cuboid of length L, breadth B, and height h is the product of length, breadth, and height. That is, V is equal to L into B into h. If the length, breadth, and height are equal, a cube is formed. Let A be the length of each side of the cube. Then, its volume V is equal to A into A into A, or A cube. The volume of a sphere of radius r is 4 by 3 into pi r cube. The volume of a cylinder of height h and radius of base r is pi into r square h. The volume of a cone of height h and radius of base r is 1 by 3 into pi r square h. Thus, by using these formulae, we can find the volume of regular shaped solids. If a solid object has an irregular shape, a stone, for example, then its volume can be measured in two ways. One is by using a measuring cylinder, and the other one is by using an overflow jar. Let us see how to measure the volume of an irregular object with the measuring cylinder. Take a measuring cylinder and fill it with water up to a certain level. Note down the volume of water by placing the eye at the level of lower meniscus. Let this volume be V1. Now tie the given irregular solid object to a thin long thread. Lower the solid object slowly into the cylinder so that the object is completely immersed in the water. The level of the water in the measuring cylinder rises. Note down the volume of water again. Let this volume be V2. Thus, the volume of the irregular object is equal to the difference between V2 and V1. If the given irregular object is lighter than water, then a heavy solid insoluble in water, such as a piece of stone or metal, is used along with the given object. This heavy solid is called a sinker. Subtract the volume of the sinker from the increase in the volume of water to get the volume of the lighter object alone. Let us now measure the volume with an overflow jar. An overflow jar consists of a vessel with an outlet or spout. Fill the overflow jar with water till the level of the water reaches the spout. Take a measuring cylinder and place it below the spout of the overflow jar. Now, tie the given irregular object to a thin long thread. Gently lower the irregular object into the overflow jar. The irregular object displaces some water from the overflow jar into the measuring cylinder through the spout. The volume of the water displaced is the volume of the irregular object. This method is called displacement method. If the solid is soluble in water, then use a liquid in which the solid is insoluble. Here is a conversion table for the units of volume.
Motion and its types, right? Now, let's go a step further in our exploration of motion. At the end of this lesson, you will be able to differentiate between slow and fast motion, identify the methods to measure time, identify the units for time and speed, measure the speed of an object, and compare the speed of two objects. James and his dad are on their way home from a drive. There are some races taking place in the playground nearby.
Hey Dad, those boys are running a race. That guy in the red t-shirt is really fast. There, he won the race.
Hey James, did you enjoy the race?
Yes, I did. But who are you? Your face looks familiar.
I am Miss Clockwork. I keep track of time. For example, I can make out who was fast and who was slow in the race.
How's that? I can easily make out who's fast myself.
Well, how do you determine speed? By measuring the distance traveled by each person in a given time, right?
Well, yes.
So, an object that covers less distance in a given time is said to be moving slow. On the other hand, the one that covers more distance in the same time is said to be moving fast.
She's talking about me. Time and speed are related, you know.
In other words, the speed of an object is the distance covered by it in a unit time. It can be calculated using the expression speed is equal to distance divided by time. Objects are considered to be in slow or fast motion depending on the speed of their motion. You saw what happened in the race, right? How was the winner chosen?
It was the participant who crossed the finish line first.
So the person who covered the given distance in the shortest time won the race.
Right. Oof, the traffic. The car's moving so slowly.
Yes. This traffic makes it difficult for the car to maintain a steady speed. What you see now is non-uniform motion of the car.
Non-uniform motion?
Yeah. We were able to increase the speed when the traffic cleared a bit. But now we're back at 5 kilometers per hour. The speedometer needle is showing a different reading every minute.
An object moving along a straight line is said to be in non-uniform motion if its speed keeps varying.
So, by the same logic, objects that maintain the same speed throughout the distance covered along a straight line are in uniform motion, right?
Yes, you got it. Right now, we're doing about 10 kilometers per hour. It will take us another 15 minutes to get home.
How can you determine what speed we're at? With non-uniform motion, the speed is changing every minute.
You're right. But it is possible to determine the average speed of the car. If we calculate the ratio of the total distance covered and the total time taken by a moving object, we arrive at the average speed for the object. I used the average speed to find out how much time it might take us to get home.
Did you get what Speedo and Miss Clockwork were talking about?
So, do you know what your average speed over the trip was?
Well, let me see. I need to know the distance and the time taken. We traveled about 35 kilometers. How long did we take to get home?
You can take help from Miss Clockwork. That's her mission in life, measuring and telling time.
That's true. We started back at about 11:30, James, and now it's 12:30.
So we took 1 hour to get home. Therefore, our average speed overall on the return journey was about 35 kilometers per hour. Right?
Right. That traffic jam really slowed us down. I was getting so impatient. That reminds me, I'm getting late. It's time for me to get back to the race. Guys, see you later.
I wonder what people did when there were no clocks. How did they measure time?
Before I was born, people used events in nature to track time. For example, they tracked sunrise and sunset. The different shapes of the moon also served as an indicator of the time of the month. And, of course, seasons repeat every year to tell us what time of the year it is. So, based on the seasons and other periodic events in nature, the months and the years were measured. I represent the modern clock. However, in the past, my ancestors existed in several different forms. Remember your trip to Delhi during your last winter vacations? You went to see the Jantar Mantar, which is basically a sun clock.
Oh yes, I remember. I read on the internet that water clocks and sand clocks have also been used to measure time in the past. Different designs of these devices were developed in different parts of the world. Here, I'll show you a different type of a clock. Isn't this beautiful?
That's a simple pendulum clock. This clock shows time based on the motion of the pendulum.
I can see that. The pendulum displays periodic motion.
Right. You can see that the pendulum of the clock is oscillating. In fact, all mechanical clocks use some kind of oscillatory motion to measure time.
How does it translate into time though?
The working of a clock is complex. It is based on the time period of the pendulum.
Time period of the pendulum? What's that?
I'll show you what I mean. Let's find a small metallic ball, a bob with a hook, a string about 1 meter in length, a stand, and a stop clock. Tie the string to the metal ball and suspend it from the stand. Now pull the metal ball to one side gently and release the ball.
It's moving to and fro, like the pendulum in a clock.
This to and fro motion of a simple pendulum is an example of a periodic or an oscillatory motion. When the bob is moving to and fro, note the farthest point. It reaches on the left and the right sides before it swings back. Let the extreme point the bob reaches on the left be X, and the extreme point on the right be Z. When the pendulum moves from its mean position Y and goes to X to Z, and back to its mean position Y, then the metal ball is considered to have completed an oscillation. Similarly, the motion of the pendulum bob, when measured starting from X till it reaches Z and then back to X, is an oscillation.
Okay. And how is oscillation related to time period?
Yes, I'm coming to that. I am bringing the suspended metal ball to a position of rest. Now, let's pull the ball to one side, say towards X, and release it, and start the stop clock simultaneously. Count the time taken for 20 complete oscillations. So, can you figure out how to calculate the time taken for one oscillation?
Sure. The stop clock shows 40 seconds. We can divide this reading by 20 to get the time taken for one oscillation.
Very good. Your result is the time period of the pendulum that we created. Thus, the time taken by the pendulum to complete one oscillation is called its time period.
So, the time period for this pendulum is 2 seconds.
Right. Galileo observed that a pendulum of a given length has the same time period. The invention of pendulum clocks was the result of this observation. Modifications to the pendulum clock helped develop winding clocks and wristwatches.
Hey, but you don't have a pendulum. Why?
Good question. Like most modern clocks, I am a quartz clock. In fact, I am more accurate than the other clocks because of an electronic oscillator in me, which is regulated by a quartz crystal.
So we generally measure time in seconds. When would we use minutes or hours?
The unit that you choose depends on your need. For example, try measuring your age in minutes or hours.
That would be tough.
Exactly. It is convenient to express your age in years rather than in days or hours. However, if I ask you how much time it takes you to get home from school, which unit would you use?
Minutes, I suppose. It takes me about 20 minutes to get home from school.
So, you wouldn't measure that time in years, right?
Right. What about speed? I guess the unit of speed would be related to the unit for time.
Well, yes. Remember the formula for speed?
Speed is distance divided by time.
Right. The basic unit of time is second, and that of distance is meter. Therefore, the basic unit of speed is meter per second. Of course, it could also be expressed in other units, such as meter per minute or kilometer per hour.
Okay. So I could say our speed on the trip back was about 50 kilometers per hour.
Yes, that's right. It is important to remember that the symbols for all units are written in singular. For example, we write 50 kilometer for 50 kilometer and not 50 kilometers. Or 8 centimeter for 8 centimeter and not 8 centimeters.
Did you know? Archaeological excavations show that the moon was used to calculate time nearly 10,000 years ago.
We spoke about how to measure the time period of a pendulum. Similarly, speed can also be measured.
I know. The meter fixed in the car tells me the speed of the car.
Yes, you are right. The meter is called the speedometer.
But there is a number display in the speedometer as well. Wonder what that is.
Shh! Talking about me?
Hey, Speedo. So, the races are over? James is wondering why you have a second number display on you.
Good observation. That meter is an odometer. That tracks the distance covered by the car.
Unfortunately, my bicycle doesn't come with a speedometer.
Not all moving vehicles and objects have a speedometer or an odometer. In cases like that of your bicycle, we calculate the speed of the objects manually.
So can we calculate the speed of Dennis's winding toy?
Why not? Get the stopwatch and a piece of chalk.
Here you are.
Let's start by marking a line at the starting point on the floor. Mark another line at a distance of 5 meters away from the starting line. The second line is the finish line.
Okay, done.
Now, wind the toy completely and put it down, a little behind the start line. Make sure you start the stop clock as soon as the toy touches the start line. We'll stop the timer when the toy touches the finish line. There! What's the reading on the stopwatch?
It reads 20 seconds.
Cool! So now we can use the formula for speed to determine the speed of the toy. Speed is the ratio of the distance travelled by the toy, which is 5 meters to the time noted on the stop clock, which is 20 seconds. Therefore, the speed of the toy is 1/4 meter per second. The basic unit of speed is meter per second. However, generally, large speeds are measured in kilometer per hour.
Can we also find the distance covered by an object in motion?
Yes, of course.
Provided the object maintains uniform motion throughout its journey. In such cases, the distance covered by the object will be the product of its speed and the time traveled by it.
Got it.
Did you know the speed of a maglev train is about 500 kilometers an hour?
Speed varies from one object to another. These objects can be animate or inanimate.
Yes, I have read that the cheetah is the fastest animal on the earth.
Yes, that's right. It can move with a speed of nearly 112 km per hour. Do you know the speed of the giant tortoise?
Not really.
It moves at a speed of nearly 0.27 km an hour. Can you calculate how fast is the cheetah as compared to the tortoise?
Let me calculate. The speed of the cheetah is approximately 112 km per hour, while the speed of the giant tortoise is 0.27 km per hour. The speed of the cheetah is approximately 415 times that of the giant tortoise.
Yes, that's right.
Did you know the average speed of a human being is approximately 40 kilometers per hour? This brings us to the end of this lesson on speed and time. In this lesson, you learn to differentiate between slow and fast motion, describe methods to measure time, identify the units for time and speed, measure the speed of an object, and compare the speeds of two objects.
You must have seen wall clocks with pendulums. You also know that the motion of a simple pendulum describes oscillatory motion. Let us discuss the simple pendulum and the terms associated with it. When a simple pendulum is undisturbed or left free, it comes to rest at a position. This position is called the mean position or equilibrium position. There are two positions on either side of the mean position where the bob changes its direction of motion. These positions are called the extreme positions. During these oscillations, the maximum displacement of the pendulum, that is, the displacement between the mean position and the extreme position, is called its amplitude. Generally, amplitude is represented by A. In a simple pendulum, the distance between the point of suspension and the center of gravity of the metal bob is called the length of the pendulum or its effective length. It is denoted by L. The bob of the pendulum moves to and fro along the same path and passes through the mean position. This is called oscillation. The number of oscillations made by the pendulum in 1 second is called its frequency of oscillation. It is denoted by F or nu, and it is measured in hertz. The time taken by the oscillating pendulum to make one complete oscillation is called its time period and is represented by T, and it is measured in second. Let us now discuss the laws governing the time period of a simple pendulum. The first law of the simple pendulum states that the period of oscillation of a simple pendulum of constant length is independent of its amplitude, provided the amplitude is small. Let us conduct an activity to verify the first law of the simple pendulum. To verify the first law, the apparatus required is a metallic bob, a thin and strong thread of length around 120 cm, an iron stand with a clamp, a cork vertically cut into 2 parts, a meter scale, and a stopwatch. Place the iron stand over a table. Tie the metallic bob to the thread and suspend it from the stand with the help of the cork and clamp. The simple pendulum is set up. Choose a length for the pendulum, say 50 cm. Pull the bob to a side such that the amplitude is about 10 cm and allow the pendulum to oscillate. When the bob is at one of the extreme positions, stop the stopwatch. Count 20 oscillations and stop the stopwatch. Note the time taken for 20 oscillations. Calculate the time taken for one oscillation, which is the time period of oscillation. Tabulate the readings. Now repeat the procedure with amplitudes of 15 cm and 25 cm. Don't change the length of the pendulum. Tabulate the readings again. You will observe that the time period of oscillation remains the same for different amplitudes. Thus, the period of oscillation is independent of amplitude, provided the amplitudes are small. This verifies the first law. The second law of the simple pendulum states that the period of oscillation of a simple pendulum of constant length is independent of the size, shape, mass, and material of the bob, provided it is not very light, such as a cork. Let us verify the second law of the simple pendulum. Take 3 bobs of different masses and different materials. Set up a simple pendulum with the first bob for a fixed length, say 50 cm. Choose any amplitude, say 5 cm, and pull the bob to a side. Now release the bob and make it oscillate. Start the stopwatch when the bob is at one of its extreme positions. Count 20 oscillations and stop the stopwatch. Note the time taken for 20 oscillations. Calculate the time taken for one oscillation, which gives the time period of the pendulum. Tabulate the readings. Now, repeat the procedure with the second bob and the third bob by keeping the length of the pendulum and the amplitude the same. Then tabulate the readings. You will observe that the period of oscillation does not change with the mass and material of the bob, provided the length of the pendulum and amplitude are constant. This verifies the second law. The third law of the simple pendulum states that the time period of oscillation of a simple pendulum is directly proportional to the square root of its length for a given place. That is, T is directly proportional to square root of L. Let this be equation 1. Equation 1 can be written as square root of L by T is constant. On squaring the equation, we get L by T square is constant. Let us now verify the third law of the simple pendulum. Set up the pendulum with a metallic bob as in the experiment to verify the first law. Select a length, say 50 centimeter. Pull the bob to a side such that the amplitude of the pendulum is not greater than 5 centimeter, and then release it. The pendulum starts oscillating. Stop the stopwatch when the bob is at one of its extreme positions. Count 20 oscillations and stop the stopwatch. Note the time taken for 20 oscillations and tabulate the readings under the head trial 1. Repeat the procedure with the same length and amplitude. Note the time taken for 20 oscillations and tabulate the readings under the head trial 2, trial 3, and so on. Calculate the average time taken for 20 oscillations and determine the time taken for one oscillation. Tabulate the readings. Now find the value of L by T square for the given length of the pendulum. Now increase the length of the pendulum by about 10 centimeter and repeat the procedure to find the value of L by T square. Repeat the procedure 3 or 4 times by increasing the length of the pendulum by 10 centimeter every time. Tabulate the readings. You will observe that the time period of the pendulum increases with its length, and the value of L by T square is the same in all the cases. This verifies the third law. Thus, based on the laws of the simple pendulum and experimental results, the time period of a simple pendulum is given as T is equal to 2 pi into square root of L by G. Let this be equation 2. From equation 2, we can write the relation between the time period of a pendulum and acceleration due to gravity as the time period of a simple pendulum is inversely proportional to the square root of acceleration due to gravity, provided the length of the pendulum is constant. That is, T is inversely proportional to square root of G. This relation is referred to as the fourth law of the simple pendulum. Since the time period of a simple pendulum depends on its length and acceleration due to gravity at a given place, it is used to measure time in clocks that work on the principle of the simple pendulum. Let us now conduct an experiment to find the time period of a simple pendulum and verify the effect of length on it. The apparatus required are a metallic bob, an unspun thread of length about 120 centimeters, an iron stand with a clamp, a cork vertically cut into 2 equal parts, a meter scale, and a stopwatch. First, find the diameter of the bob using an ordinary scale or vernier calipers. Calculate the radius r of the bob by dividing the diameter by 2. Place the iron stand over an experimental table. Tie the bob to the thread and suspend it from the stand with the help of the cork and clamp, such that the simple pendulum is set up. Now measure the length of the pendulum from the point of suspension to the bottom of the metallic bob using the meter scale. Let this be L1. Calculate the effective length of the pendulum by subtracting the radius of the bob from the measured length L1. That is, L is equal to L1 minus R. Pull the bob of the pendulum to one side such that it makes an angle of about 5 to 10 degrees with the vertical, and then release it. Start the stopwatch when the bob of the pendulum is at one of the extreme positions. Count 20 oscillations and stop the stopwatch. Note down the time taken for 20 oscillations. Let this be T. Here, the time taken for 20 oscillations is noted to minimize the error in calculating the time taken for one oscillation. Time period T1 is equal to the time taken for 20 oscillations divided by 20. On the other hand, substitute the value of L and G in the formula for the time period of a simple pendulum and calculate the time period. Compare the experimental value and the calculated value of time period. It is observed that the two values are approximately equal. If the time period of a simple pendulum is 2 seconds, then the pendulum is called a seconds pendulum. If we take the time period as 2 seconds and acceleration due to gravity as 9.8 meters per second square, then the length of the seconds pendulum works out to 1 meter or 100 centimeters. On squaring the equation for the time period of a simple pendulum, we get T square is equal to 4 pi square into L by G. At a given place, acceleration due to gravity G is constant, and therefore 4 pi square is also constant. Hence, T square is proportional to L. It is also used to determine the acceleration due to gravity at a place.
You already know that the time period of a pendulum is given by the formula T is equal to 2 pi into square root L upon G, where L is the length of the pendulum and G is the acceleration due to gravity at a given place. Let this be equation 1. From this equation, it is clear that the time period of a simple pendulum depends on the length of the pendulum. The relationship is given as T is directly proportional to square root of L, since 2 pi and G are constant at a given place. Squaring both the sides, we get T square is directly proportional to L, which can be rewritten as T square upon L is equal to constant. To understand how the square of time period depends on length, let us perform an experiment. Consider a simple pendulum of length 40 centimeters fixed to an iron stand. Pull the bob to a side such that the amplitude is not greater than 5 centimeters. Release the bob. The pendulum starts oscillating. Start the stopwatch when the pendulum is at one of the extreme positions. Stop the stopwatch after 10 oscillations. Note the time required for 10 oscillations. Based on these readings, determine the time required for one oscillation, which is the time period of the pendulum. Note the time period. Calculate the value of t square also for the length of the pendulum. Next, increase the length of the pendulum by 10 centimeters and repeat the procedure to find the value of t square. Repeat the procedure 3 or 4 times by increasing the length by 10 centimeters every time. Record the readings and the values of t square for each length. You will observe that the time period of the pendulum increases with an increase in its length. However, the readings do not indicate the exact nature of dependence. A graphical representation of L and t square can give a clear picture of the exact relationship. So, plot a graph between L and t square by taking length on the x-axis and the values of t square on the y-axis. You will get a straight line. This straight line shows there is a linear relationship between L and t square. The slope of this straight line is given by S is equal to vertical change upon horizontal change. It can be written as S is equal to t square upon L. Let this be equation 2. Squaring equation 1 on both sides and simplifying, we get t square upon L is equal to 4 pi square upon g. Let this be equation 3. Using equations 2 and 3, you can write S is equal to 4 pi square upon g. Rewriting this equation, we get g is equal to 4 pi square upon S. Let this be equation 4. From the graph, the slope of the straight line is obtained by considering 2 points P and Q on this line as far away from each other as possible. The coordinates of P are 0.4, 1.61 and of Q are 0.7, 2.82. Now, using the slope formula, we get the value of S as 4.03. Substituting the value of S in equation 4, we get G is equal to 9.78 meters per second square. In this way, we can calculate the value of G using a simple pendulum.
The mass of an object is defined as the amount of matter present in it and is denoted by m. Mass is a physical quantity which is independent of other physical quantities. Thus, mass is a fundamental physical quantity. The CGS unit for mass is gram, and its SI unit is kilogram. 1 kilogram is defined as the mass of a cylindrical piece of platinum-iridium alloy kept in the International Bureau of Weights and Measures at Sèvres near Paris. Very often the term weight is used instead of mass. However, weight and mass are different. The weight of an object is defined as the force with which the object is attracted by the earth. The weight of an object varies from place to place, whereas its mass is always constant. It does not change with position or place. The mass of an object is measured by a common balance by comparing it with a known standard mass. To understand the principle of a common balance, let us conduct an experiment using a meter scale. Take a meter scale. Suspend it from its center, the 50 centimeter mark, by means of a thread such that it is horizontal. Mark the center of the scale as O. Suspend a known mass M on the left side of the scale at some distance from the center, say at the 10 centimeter mark, such that the scale tilts towards the left side about center O. Now take another identical body of the same mass M and suspend it on the right side of the scale at some distance from the center, say at the 80 centimeter mark, such that the scale slowly changes its orientation. If the mass M on the right hand side is shifted from the 80 centimeter mark to the 95 centimeter mark, then the scale tilts slightly towards the right. Now shift the mass M on the right hand side from the 95 centimeter mark to the 90 centimeter mark. The scale orients along the horizontal. That is, the scale remains horizontal when two objects of equal masses are suspended at equal distances from the point about which the scale is free to tilt. The point about which the scale is free to tilt is referred to as the fulcrum. The same principle is used in the common balance. The common balance consists of a horizontal beam with a pointer in the middle. The beam is free to tilt about its center point, which is the fulcrum. Two pans are suspended on either side of the pointer at equal distances. To measure the mass of a body, standard masses with different values are available. The body whose mass is to be determined is placed in the left pan, and the standard masses are added to the right pan until the pointer comes to the center, and the beam remains horizontal. In such a situation, the sum of the standard masses gives the mass of the object. However, for an accurate measure of mass in a laboratory, a common balance is not useful. In such cases, a physical balance is used, which can measure mass up to 1 milligram accurately. Nowadays, electronic balances are used to measure mass. These display readings up to 1 milligram accurately. There are different units to measure the mass of different objects. The table here gives the relation between different units of mass. You know that the mass of a body is the amount of matter present in it. The mass of a body is always constant, and its SI unit is the kilogram. Generally, the mass of a body is measured using a common balance by comparing it with standard masses. In the laboratory, the mass of a body is measured with a physical balance that can measure up to 1 milligram accurately. Let us now see the parts of a physical balance. The physical balance consists of a light and rigid beam of brass. The beam is mounted at its center on a knife edge, resting on a steel plane surface at the top of a metallic pillar. The pillar is fixed to a wooden base. Two knife edges at each end of the beam support stirrups, from which two pans of equal masses are suspended. A long metallic pointer is attached perpendicular to the beam at its center, pointing downwards. The pointer moves over an ivory scale fixed at the bottom of the pillar. The pointer coincides with the central point on the scale for empty pans when the masses of the two pans are equal. The beam can be released or arrested by turning a handle attached to the wooden base below the pillar. To avoid wear and tear of the knife edges, the beam of the balance is made to rest on the rigid metal support fixed to the pillar. The beam is then set to be arrested. The ends of the beam are provided with two adjustable screw nuts. The beam can be made to oscillate symmetrically about the central point on the scale by adjusting the position of these nuts. The wooden base of the balance rests on three leveling screws. A plumb line is suspended from the metal support on the top of the pillar. An index is provided at the base of the pillar. By adjusting the leveling screws at the base, the plumb line is made to coincide with the index such that the base of the balance is horizontal. The whole device is enclosed in a wooden box provided with glass doors to avoid the effect of air or wind. The balance comes with a weight box containing standard weights of gram weights and milligram weights. The weight box is also provided with a pair of forceps that are to be used to handle the weights. The weights are not to be touched with the hands. Let us now see how to use the balance to measure the mass of an object. Before using the physical balance, the plumb line is made to coincide with the index by adjusting the leveling screws at the base. The beam is then raised gently by using the handle to ensure that the pointer oscillates equally on either side of the central point on the scale. If it does not, then the screw nuts provided on the beam are adjusted to make the pointer oscillate equally about the central point on the scale. During the oscillations, the extreme positions on the scale where the pointer turns back are called the turning points. The division on the scale where the pointer comes to rest after the oscillations is called the resting point. The resting point with empty pans is called the zero resting point or ZRP. To calculate the zero resting point, release the beam using the handle and allow it to oscillate twice or thrice. Then, note the successive values of 3 turning points on the left and 2 turning points on the right. Let the 3 readings on the left turning points be L1, L2, and L3. Let the 2 readings on the right turning points be R1 and R2. Take the average of the readings on the left turning points. Let this be L. Similarly, take the average of the readings on the right turning points. Let this be R. Now calculate the average of the mean turning points, which give the zero resting position of the balance. Now, arrest the beam by using the handle. Open the door and place the body that has to be weighed in the left pan. Place some of the standard weights in the middle of the right pan with the help of the forceps. Close the door, release the beam, and find the oscillations of the beam. If the weights are in excess, then arrest the beam, open the door, and try the next smaller one, and so on until the body is counterbalanced by the weights. When the beam is released, the pointer oscillates to about the same extent on either side of the zero resting point. Then, note the standard weights and find the resting point RP. If the resting point coincides with the zero resting point, then the mass at the resting point gives the correct mass of the body. If the resting point is greater than the zero resting point, then it is called a higher resting point or HRP. If the resting point is a higher resting point, add 10 milligrams in succession until you get a resting point less than the zero resting point. If the resting point is less than the zero resting point, it is called a lower resting point or LRP. If the resting point is a lower resting point, then remove 10 milligrams in succession until you get a higher resting point. Find which one of the two resting points is nearer the zero resting point. The corresponding standard weights give the mass of the body correct to a centigram. Let us calculate the mass of a given body correct to a milligram. Mass of the body correct to a milligram is equal to mass at higher resting point plus p gram or mass at lower resting point minus p gram. Since 10 milligram, which is equal to 0.01 gram, is the smallest weight that can be added to the pan or removed from it, we can write it as mass to be added to the mass at HRP is P is equal to 0.01 into HRP minus ZRP by HRP minus LRP gram. In other words, the mass to be subtracted from the mass at the LRP is P is equal to 0.01 into ZRP minus LRP by HRP minus LRP gram. By adding or subtracting the values of P to the mass at HRP or LRP respectively, we will get the mass of the body correct to a milligram.